Okay, so in this question, you have a reducing elbow used to deflect water flow at a rate of 30 kg per second in a horizontal pipe outward by a angle theta equals to 45 degree from the flow direction while accelerating it. The elbow discharges water into the atmosphere. The cross-sectional area of the elbow is 150 cm square at the inlet and 25 cm square at the exit. The elevation difference between the center of the exit and the inlet is 40 cm. The mass of the elbow and the water is 50 kg. Determine the anchoring force needed to hold the elbow in place. Okay, take the momentum flux correction factor to be 1.03. Okay, so we will take the elbow as the control volume. Okay, so this is the control volume. And then we take the inlet and the outlet. Okay, inlet as 1 and outlet as 2. And then the anchoring force is represented by FRZ and FRX. Okay, where the FR we have divided it into 2 to FRX and FRZ. Okay, so now we will apply the continuity equation where the mass flow rate is constant. So the mass flow rate at the inlet is equals to the mass flow rate at the outlet, which is the mass flow rate given, which is 30 kg per second. Okay, mass flow rate is equals to rho AV. So V is the velocity. We can find the velocity at 1 and velocity at 2 here using this formula. Okay, so velocity at inlet is equals to m dot over rho A1. So 30 divided by 1000 times the area, which is 150 cm square equals to 0.015 meter square. So the velocity is 2 meter per second. And at V2, same, we will use the same formula, and then we will substitute the given values, and we will get the velocity is equals to 12 meter per second. So we can see here the elbow has increased the velocity from inlet 2 meter per second to 12 meter per second due to the change in the area of the pipe. Okay, now we will use the Bernoulli equation to solve for the pressure to find the force. Okay, so at the inlet we have P1 over rho G plus V1 square over 2G plus Z1 equals to P2 over rho G plus V2 square over 2G plus Z2. Okay, we will take Z1 at inlet as 0 and Z2 at the outlet. Okay, that will be equals to 40 centimeter. And for the pressure, we have pressure at the outlet, we have pressure inlet and pressure outlet. Pressure at the outlet is the same as the atmospheric pressure. Okay, so that is atmospheric pressure. Pressure 1 minus pressure 2 is equals to pressure 1 minus the atmospheric pressure. So that is equals to pressure gauge at the inlet. Okay, so we want to simplify this Bernoulli equation. Z1 is equals to 0. And then we can write it again as P1 minus P2 is equals to rho G times with V2 square minus V1 square over 2G plus Z2 minus Z1. And we get P1 minus P2 is P1 gauge, that is equals to 1000 times 9.81 times 12 square minus 2 square over 2G. Okay, and then plus 0.4. So we get the pressure at inlet, gauge pressure at inlet is equals to 73,900 Newton per meter cube. Okay, we want to use the momentum equation for steady one-dimensional flow. Okay, where the total force is equals to the total momentum from outlet minus total momentum going in. Okay. So we will write this equation for at the x-axis. Okay, Frx plus P1 gauge times A is equals to beta m dot V2 cos theta minus beta m dot V1. Okay, and then we solve, so Frz in the z-axis, so that was in x-axis. Okay, in the z-axis we have Frz minus W is equals to beta m dot V2 sin theta. Now we solve for Frx and Frz. Okay, we substitute the values that we are given, and we get Frx equals to 1.03 times 80 times 12 cos 45 minus 2 minus 73.9 divided by 0.015. Okay, so that equals to negative 0.908 kilonewton. And then for Frz, okay, we use the same method, and we get Frz equals to 1.03 times 30 times 12 sin 45 plus 490.5 Newton. And that's equals to 0.753 kilonewton. So Fr, the anchoring force, is equals to Frx square plus Frz square square root. Okay, we get 1.18 kilonewton, and the angle theta is tan Frz over Frx equals to tan 0.753 divided by 0.908. We get negative 39.7 degree. So the anchoring force is given as 1.18 kilonewton at the angle of negative 39.7. So if we go back to the elbow, the anchoring force is actually located like something like this lah. Okay, at the inlet. So alright, so because the angle is negative, right? Okay.